We are going to carry on now with transformers. So that's our next chapter. And there we go. There's okay, principle of operation of transformers, and this thing called useful and leakage flux, magnetic flux. Now we use that to build an equivalent circuit with transformers, for transformers, and then we'll see when we use transformers in parallel with each other. All right, so transformers, basically the main use of it is to change the voltage in a let's say a power distribution center, a system. Okay, so you have an input, a primary side of the transformer, where you on this side you'll have an AC voltage. So there's VAC, that's your input, primary, and that consists of the windings, insulated windings, so they make no electrical contact with this core over here, magnetic core. Then on the secondary side, or the output, then you'll also get AC waveform there of the voltage. So this one at the moment on the secondary side, the terminals there, that's open circuit. So there's no load connected yet. Okay, and that's called the secondary winding. And depending on the ratio of the turns, so if this is N1, the number of turns on the primary, then the number of turns on the secondary, depending on that, gives you your voltage ratio. Okay, so we use it to step the voltage on the secondary up and down. All right, so the link between this primary and secondary current is this magnetic flux. And yeah, that is concentrated into the core, into this magnetic material. And of course, that magnetic flux is fluctuating at a frequency F, the same as the frequency of the input. Okay, and because of that, it induces, by means of Faraday's law, it induces a voltage in the secondary windings. So we across here at the moment, we have a voltage here, and we call that E2, E being the EMF induced voltage. Okay. So when it's on open circuit, as we saw in the last diagram, pretty much exactly what you see here, hey? You have this magnetic core which concentrates the magnetic flux in there. But you'd think that if there was this situation on open circuit here, hey? So the current in the secondary winding is zero. So we call this I2. And at this stage, 0 amps, because it's open circuit. So there's no load there. We haven't closed the circuit. That doesn't mean you don't get your voltage. You're still inducing the voltage across the windings, but you haven't closed the loop, so there's no current. Okay, which means this little current here, IO, flows even though there's no current in the secondary. So what does that do? That current is providing the energy required to build up this magnetic flux. So you need that small current there. It's not very big compared to the full load current once you connect a load. So we call this E2 the secondary open circuit voltage, because across the terminals here, you're also going to measure this E2. All right, when the transformer is on load now, you can see now you have a finite current flowing in that secondary circuit. Okay, now you have your primary current now will get bigger as a result of I2 getting bigger. So it's not like you inject a current in here and then you sort of find a place for the current to go on the secondary. the load, the magnitude and the nature of the load on the secondary draws a certain current, and because it requires energy, the I1 responds to that I2 drawing the current. Okay, so all of the energy going from I1 to I2 entirely is transferred magnetically from the primary to the secondary. There's no electrical connections. The primary and secondary are totally isolated from each other. All right, we need to know about this thing called useful and leakage flux. So useful flux is this flux here, which links between the primary and secondary windings, and then it transfers that energy to the secondary. Leakage flux, this happens because you've got current flowing now, I1 and I2, and that, because you've got current in those windings, that's going to set up their own magnetic fields, and you can see them over here, and some of it leaks out of the transformer here, you see, and a second magnetic field. All right, so it's not the one that is concentrated in the core. It's wasted. It's leakage flux. So we have to take that into account, because it has an effect. This leakage flux induces it. You see, it's not static. It's pulsating at a frequency f, the same as this, and it induces a second EMF, a back EMF in these windings. So it opposes the current. So we have to take this. We have to take this concept into account. Hey? So that is leakage flux here. So you get leakage flux in the primary, and you get leakage flux in the secondary, and so the leakage reactance is how we model it. So we, instead of trying to put that into the transformer, actually, we assume an ideal transformer here, and then we put these pieces in the primary and the secondary, and that takes into account the effect of this leakage flux. Okay, so we're trying to model this transformer. So you also have resistance in these windings. It's small, but it's finite, and we have to take it into account. So in these windings over here, they have a finite resistance. So we model it there. Remember, we're assuming an ideal transformer here. So we model these imperfections here and showing them as like a resistance and an inductance, just to build up a model, okay? So they're actually internal to the windings, but we just show them like that. So you've got primary resistance, primary reactance, secondary resistance, and secondary reactance as well. So we're starting to build up a model there, right? Now, the methods of reducing the leakage flux, and they like to sometimes ask you this, what are the ways to reduce leakage flux? And it's generally like just a structural thing, it's not like a circuit that you change. So what you do, you make the transformer window long and narrow. I showed you like a square looking transformer there. Hey? But if you make this window long and narrow like this, it's probably due to trial and error they found this out. There's your primary winding, and here's your secondary winding. Oops. Hope it looks better than that. But you can see now the ratio of the width to the height has changed. So if you make it longer and narrower, it tends to decrease the leakage flux. So you can arrange the primary and secondary windings concentrically. So which one? Let's say this was a 1,000-volt transformer, and the secondary is 400 volts. So this would be then the high voltage side, and this would be the low voltage side. So what you do is you wind the windings, instead of showing it like that, you wind the low voltage windings close to the core, and you wind the high voltage windings on top of it. I'm sure a lot of trial and error went into all of this. Sandwich windings, so the primary windings, you put them in two sections, one on each limb. So here's your primary windings. So you wind them around here and here, and then you sandwich them in between the secondary windings. Or the last one, the shell type construction. So this one always makes the most sense to me. So you see, it's instead of that square, you've got something with like a pillar in the middle, eh? And then you wind these around that pillar. So here's your primary windings, and then they kind of get sandwiched there between the secondary windings, and they wind around this kind of pillar. If you can see there's not very much room for this flux to escape, if you want to put it in simple terms. All right, so now with the transformer on load, okay. So this is going to be our equivalent circuit of the transformer, right? So you can see here, we've got the resistance and reactance of the secondary. That's our V2, the terminal voltage. When you go on load and you get I2 flowing in here, what happens? I2 flows through this impedance, this internal impedance of the secondary. So if you've got I2 flowing through Z2, then you get a volt drop across Z2. V2, the terminal voltage, is no longer equal to E2. It will equal E2 when you're on no load, but now if you connect this through a load like that, ZL, you see, now you get I2 flowing through the internal impedance, and the output voltage is, the terminal voltage is going to be different. Okay, so what is this parallel thing here in the middle? That is, remember I said IO. IO is the primary no load, primary no load current. Okay, so that's that little current that flows even when there's no current going through I2. So now it's made up of two components. So you can see that's why you've got this parallel section. I'll tell you about that in a minute. If we look at the phasor diagram, we use the flux as a reference because it's linking both sides. And then in phase with the flux, the component of IO, which is in phase with the flux, we call IMAG, or the magnetizing current. And then you get this smaller IC, which is in phase with the applied voltage, V1. So this is your applied voltage. All right, and you remember the back EMFs, which were in opposition to the V1. See E1 and E2 there. The back EMFs over here are 180 degrees in opposition. They oppose the current. So, so IO has got these two components of the current, the reactive or magnetic, and the active or the small power component, which is in phase with the voltage. So there's small heat losses in that. So, and hysteresis losses. Oh, other way around. Wrong. So if that's the case, this angle, this phase angle, between the applied voltage. Oh, what happened there? That's odd. Okay. A little speed wobble there. Hey. All right. So the angle between the applied voltage and this IO is this phase angle here. The cosine of that phase angle gives you quite a bad power factor when the transformer's on no load. Okay. You don't get much in the way of calculations on this type of stuff. Not very much. They'd rather, we'll see what type of calculations you get when you unload. But there is a small calculation that we sometimes get. So if we go on load, all right, so we can see this very involved looking phasor diagram, hey? So if you looked at V1, see there's the difference between E1 and V1. Because of the volt drop across the reactive, the reactance and the resistance of the primary. And the same thing, V2 and E2 aren't equal when you unload. So these two aren't equal because of the current I2 going through R2 and the current I2 going through X2. Yeah. And then if you vectors, then you get to E2. All right. So you don't have to be able to draw that. I've never seen anybody ask you to redraw that. I'm sure you're quite relieved about that. All right. So now, when you unload, sometimes you can get a small calculation where they tell you, ignoring those volt drops, those volt drops that I just pointed out now, these ones over here. If you ignore these volt drops, so it's a calculation where only if they say ignore the volt drops that you can do this. There we go. All right. So what you have, as I said, the I2, if you get a current I2 in the secondary and you have a power factor which is set by the load, so you're going to get a phase angle. This is due to the impedance ZL, the load impedance, because that'll have a magnitude like magnitude Z at some angle theta ohms or phi 2 ohms, and this gives this angle. So if we're given this I2 and this angle, you're able to work out the primary current. Here's the no load current, and the current in the primary as a result of the increasing current in the secondary. So as I2 gets bigger, this I1 prime gets bigger. It's exactly 180 degrees in opposition to I2, and depending if N1 equals N2, all right, let's say they had equal number of turns, then this one would be the same, that magnitude. But if there were different turns ratio, then you have to then I1 prime will not be equal to I2. You have to do that N1 over N2 equals I2 over I1 thing to get prime like that. Okay, so then if you can get this and you get that, then you can work out I1. But you can only do the simple one if they say ignore the volt drops. So I1 will be IO and the I1 prime, okay, with the angles. Why are they minus? Because they are relative to this, eh? Funny, we normally do things from the positive x-axis, eh? But we're making the flux the reference. So the currents have to be measured relative to this voltage. So funny enough, this one, you can see all of these angles are measured from here to here, here, and here. So just watch out for that. Then, let's just do a quick one here. The current drawn by a single-phase transformer, and all your calculations are going to be on single-phase transformers. And just watch out. What kind of calculation are we doing? We're doing a no-load calculation, all right? And ignore all internal volt drops. So you have to have that and that before you can do this type of calculation. So on the transformer, 400 volts. So they say the current drawn by a transformer. That means here's your transformer. Is that the current drawn by the transformer? So is that the primary current or is that the secondary current? It is the primary current. It draws it from the power supply. Okay, so it's 400 volts, 50 hertz. All right. And they say when it's on no load, then it's 5,25 amps. In other words, this is 5,25 amps IO. And the power factor of 0.55 lagging. So the angle here is going to be, okay, phi. Yeah, and we will, phi is what? Arc cosine of 0.55. Measured from the V1, eh? All right, the load, there's our load connected here. And that is our, what do we call it? Z. Z, like that. Oops, there's Z. So for turns ratio of 1 to 5, 1 to 5, all right, then what we calculate the current drawn from the supply. In other words, how much is I1? I1. If they said the current in the load, you do a different thing. But with the current drawn from the supply is I1. So there we get our angle, phi. And then we find out what V2 is on no load. This is basically, the no load voltage. In other words, it is E2. Okay, so Z load, I just converted it to polar. And then I2 is V2 on, so I2 is V2 over Z of the load. So that's your I2. And we always then make this 0 as a reference. Relative to that 0, okay, we're going to get this current. So we've made our V2 in this, just for this calculation, 0, or E2, sorry. And then this phi2 now is going to be given by this. All right. So then, you see, it is very close to this. So this is kind of exaggerated, this I1 prime angle and this I0 angle close to each other, hey? All right, so what is the magnitude of I1 prime? It's I2 times the turns ratio. And I1 prime is then 159,535 at this angle minus 56,056. So this angle here is the same as that angle there. So this is the same as that. So we know what I0 is, and we know what I1 prime is. And they add them. That's now our primary current when you unload. Okay. So there's a couple of these in the activities that I will send you. So just do some of these. Not very common, but they do pop up every now and again. All right. So now we really, if we look at our equivalent circuit, kind of see it's a little bit complicated. I mean, really, if you look at it, what on earth are we going to do with this thing? It's very difficult to work with there. Because this, this is what we had IO. Because that IO is so small compared to the current at when you're on full load, it's about 3% of that current. That we decide when we on load that we are going to consider this effect as negligible. So we don't consider it. So now our simplified equivalent circuit looks like that, starting to take shape a little bit. So now we just have our X1, R1, X2, R2. That's all we've got left there. Then what we do is it's still difficult to work with on both sides of the transformer. So what happens if we take this R2 and this X2 here, and we do there's a process called referring. So we refer X2 to the primary, and we call it X2 prime. We refer R2 to the primary, and we call it R2 prime. Then we're going to add R1 and R2 prime, because they're in series, we can add them. Then we're going to add X1 and X2 prime, because they're also in series. So we'll do that, and then we are left with what is called the equivalent. We're going to call that, let's say, referred to the primary, so it'll be R equivalent referred to the primary will be equal to R1 plus R2 prime. And basically, to refer these across the transformer, we have to modify. We can't just take the number for X2 and put it into the primary and hope it's all going to work out. We have to do things to that X2, which I'll show you now, in order to get X2 prime. So that the effect that X2 prime has on the working of the transformer, if we put it into this primary circuit, it must be the same as the effect that X2, the magnitude of X2 had in the secondary circuit. So we have to modify it a little bit. So it goes like this. We've referred our values from the secondary to the primary, and now we merge them. RE1 equidistance is R1 plus R2 prime. So R2 prime is R2 times the turns ratio squared. So we refer to primary, therefore primary on top here. Primary over secondary, referring this way. Okay, XE1 is exactly the same. X1 plus X2 prime, again, primary over secondary. And don't forget, I've seen people forget the squared. And then your ZE1 is just RE1 plus JXE1. Now you can do the same calculation where you, instead of referring to the primary, you leave R2 and X2 in the secondary, and you refer R1 and X1 to the secondary. Then you'll get it like that. See? So then you're going to have RE2. In other words, equivalent resistance referred to the secondary. And it's just backwards. And make sure when you refer to the secondary, it's N2 over N1 squared. When you're referring to the primary, it's N1 over N2 squared. Get it there. All right, then when you have a transformer, you'll see that it's got like a nameplate on it with all data about it. And you'll see that the resistance and reactance values are more likely than not given in ohms in per unit or percentage values. So what it means is, let's say we worked out our RE1. Now our per unit value, there are no units, it's no units, so there are no ohms or anything. Okay, it's just a number. So this E epsilon R, the per unit resistance of the transformer, if you've referred everything to the primary and you get your RE1, then you multiply it by I1 over V1. And I1 and V1 are the rated values of the transformer. So that is your rated current and your rated voltage. So if the thing has a kVA rating, S equal I1 V1. So these are rated values, okay? So use those rated values, I1 and V1 there. Now, if you've referred everything instead to the secondary, you can do so. Then you get an RE2, eh? But then you must use the rated values of I2 and V2. And what is notable here is that these are equal. So you can calculate these using either value, and the per unit resistance or the per unit reactance or impedance is the same, whether you calculate it on either side. What do we use that for? So let's say we remember that complicated vector diagram or phasor diagram where we had those values in there of I1 times R1, and we had I1 times X1, and the same on the secondary. So if we want those values, then we'd have to find out what I1 is, and then we would multiply it, say, by RE1. Then we would get that voltage, the volt drop. But if you have the per unit, these per unit numbers, yeah, all you need is that per unit number, that would be your R, and multiply it by the voltage, the input voltage. And that's going to give you the same voltage as this one. If you had like your epsilon X here, you just multiply it by V1, and it's going to give you the volt drop across the X value, across the reactance in the primary. But you don't even have to know what the current is. So in practice, it's a useful number to use. And why do we need this RE1 and all these numbers? It's because, remember I said that once you've got this current I2 flowing in the secondary, we're on load now. Now, these are the terminals. So E2 is not equal to V2 anymore. So because I2 through Z2, and you're going to have a volt drop. So your terminal, put a voltmeter across the terminals, you'll see as soon as you start drawing current, the terminal voltage will start dropping. This is a definition they like to ask. Voltage regulation. What does it mean? It's all about voltage. Voltage regulation is a rise or fall of the secondary terminal voltage, V2, with the applied voltage, V1, remaining constant. So you take the voltage load, and then you open the breaker on the load, and you cut that the current through the load, and then you leave the voltmeter on V2, then you'll measure E2 instead of, whatever it was when it was on load. And that is the definition of voltage regulation. So what we need to calculate is this V2 on load is E2 this number over here, times 1 minus the per unit reg. Now, the per unit reg, I'm going to show you how we calculate that. We need those RE1s and XE1s in order to do that. So once we've got the per unit regulation, it's very easy to calculate the V2 once you unload. So we have to take into account that this load could have a leading or a lagging power factor. In other words, lagging power factor would be an inductive load, so it's probably more likely to be this one. But let's say you have a capacitive load, you would have a leading power factor, because the power factor with the transformer is set by the load. Phi 2. This is set by the load all the time, not by the transformer. All right, then here is our calculation for the per unit voltage regulation. Don't get nervous about that phasor diagram there. Now, so the per unit voltage regulation, so if we're using primary values, all right, everything referred to the primary, then it's RE1 here and XE1 here. Doesn't matter. Although we've referred to the primary, this number, it's 2. This phi 2, I showed it as phi 2, I'm showing it as theta 2, yeah, is set by the load. So it doesn't matter that we're using primary values. We always use this in the secondary, that angle in the secondary. All right. Then again, you see I1 and V1. So it's RE1, XE1. I1, V1. What are these two? These are the rated values. So we need all of that RE1 and XE1. Now, in the middle there, I've shown you this plus or minus. If this is, we're talking about this load again. If the load has a lagging power factor, this is a plus. If the load has a leading power factor, this, plus minus is a minus. So, all right, so you see 100 kVA transformer. Transformers are always rated in kVA, never in kilowatts, always in kVA. Let's just make certain we know what we're talking about there. There's your power triangle. So this is S, apparent power in V unit VA. This is P. This is true power in watts. There's a phase angle. And here is Q. This is your react AVA or VA. VA or reactive. So your apparent power, your transformer is always rated it. So this is the transformer rating. You see? So it's got 400 turns and 80 turns. So we get these numbers. Those numbers are given to us. All right. Supply voltage V1 equals 2,200 volts. So with 2,200 volts on the primary, we can work out E2 when it's on open circuit by using the N1 over N2. Okay, so we'd be able to work that out. But then what happens, they now ask, they might not even ask you to work out equivalent resistance and reactance. They might just ask you, what is V2 on load? What that means is work out the per unit regulation. That's what it's telling you. That to get the per unit regulation, you need to get RE1, XE1, or RE2 and XE2. But they're normally going to tell you which side of the transformer to refer the values. All right, so the equivalent impedance referred to the primary. So we have to take these over there. The RE1 is 0.55 ohms. The reactance is 1,95975. So these are equivalent. So it's an equivalent number describing the effect on the transformer of the resistance that have been now lumped together. Because this one, the volt drop across it is due to I2. This one, the volt drop across it is due to I1. So in order to get this one over there, you have to maneuver its value a little bit, hey? Because I1 is not equal to I2. So then we can get the impedance, right? So in order to get the per unit regulation, we don't actually need the impedance. Okay, now they tell you what is the voltage regulation and secondary terminal voltage for full load with a power factor of 0.8 lagging. Like, you cannot work this out without the power factor. So now you connected a load here and the power factor is 0.8 lagging. So that's going to give you your phi 2. So the regulation, the unit regulation. So we worked out our value of RE1 and we worked out our value of XE1. The power factor is lagging, therefore this is a plus. So the power factor is 0.8. So cosine theta phi 2 is 0.8. So if I go arc cosine of 0.8, and then I find the sine of that angle, it's going to come to 0.6. This is, yeah, that's it. So that's 0.6. Then the voltage V1, yeah, we're given that is 2,200. And I1 is, well, this is a single phase transformer. Single phase. Therefore, S equals V times I. If it was P for true power, it would be VI cosine theta. But S, this is S, P, eh? So I equals S over V. And that's typically always how you work out the current. S over 1,000 over 2,000. Let's see. What was that? 100,000. The voltage is 2,000. Lost it. 2,200. And that works out to be a current of 45,45. For some reason I left it out here. I don't know why. Don't you? All right. So now if I put all of those numbers in there, then I get my per unit regulation. This is what I need. So what I can do, I work out E. Here's my E value, E2. It's E1 or V1 times the turns ratio into N1 over E is, okay, yes, the N2 over N1. So that would be the value of E. But I want to get V on load, so V2 on load. This is an easy way of doing it. Rather do this. Is your E. You can do it like this, you get the same answer. But anyway, 1 minus per unit reg. If you do that and you use this number, so it'll be 1 minus a slight fraction. So of course V2 on load is going to be less, say. So it goes from 440 to 425,2. And the difference between those two is 14,8 volts. If you have a leading power factor, it kind of does things a little bit differently. All those numbers are exactly the same. The only thing that changes is the sign. And you will always get a negative number there. Why? Because you'll see, if you go to that calculation I do, now I've got it. Okay, if I go V2 equals E, 1 minus, and then I put a minus 0,0154. Eh? You see what I mean? 1 minus a minus, so that 1 comma a little bit. So V2 is going, you see here, instead of 440, it increases to 446. And that will always happen with a leading power factor. So if you've got a leading power factor and you get this negative number for your per unit regulation, don't get in a panic. It's meant to be like that. And this is pretty much a dead cert, for you to know. You must know this calculation. Chances of you not getting one of these is very remote. Now, power transformer ratings, remember I said, transformers are always rated in kVA. So to get the current, with the single phase transformer, it's just S equals V1 I1. You always got to get single phase transformers, okay? You can also use V2 I2 because these transformers are very high efficiency machines, like 97% or more. So you can say S, the apparent power is V1 I1, and you can work out S equals V2 I2 using the same numbers. So losses in a transformer, you get constant losses. All right, there are a little bit of losses. Constant losses are eddy current and hysteresis, basically. All right, and a little bit of dielectric losses when a very, very high voltage. The dielectrics loss. So the insulation, in other words, as well. So variable losses, these are mainly I squared R, or heat losses in the windings. Those are the ones we can really calculate. So that's why they aren't 100% efficient. Meaning, and remember with efficiency, we're not talking about comparing voltages like we did with regulation. It's P out over P in. In other words, these numbers are always in watts, not kVA, watts. You're talking about power in, and then you get some heat losses, primarily heat losses, then power out. That heat had to come from somewhere. The efficiency is determined using open circuit and short circuit tests. Now in 5, you won't have to do big calculations on these. And in 6, you do much more testing calculations. But you need to know on this, there's an open circuit test. You need to know what it is. So in other words, you've got a setup here on the open circuit test. So that means here on the secondary, it's open circuit. So all you do, you apply a voltage as a variable voltage here. You apply a certain voltage. There's a watt meter, true power, P. Watt meter there. Ammeter, so you've got your volts and currents and your, what are you going to measure here? This current? This is going to be the no load current. Remember that IO? It's that. Now in other words, the watt meter, how much power are we putting into this transformer, even though we're not connecting it to a load? So what it is it's measuring the power going into this transformer is primarily measuring the core losses in the transformer or the constant losses. All this slight heat losses and the dielectric losses at very high voltages. So those are constant losses. That's why you do the open circuit test. So you measure it on the watt meter. This part I just added in, okay? You just need to really to know that and this. Know how to draw that little sketch, okay? That little circuit. Now you also do the short circuit test. Short circuit test is very much the same, eh? Except they're the terminals of the transformer. We short circuit it. We short circuit those terminals. That means on the primary, we better start at a very, very, very small voltage. So we have this variable voltage here. We started up at very low voltage because you shorted the terminals on the secondary now. So the only thing opposing the current in these windings is the impedance of these windings. That's all. So you better not. There's no load here to oppose the current in the secondary. So what we do, we tweak this until this voltage gets to rate the certain reduced voltage. There'll be a much voltage to the rated voltage, reduced voltage, and at that very reduced voltage, we tweak it until we get rated current flowing. So this rated current will flow at a much reduced applied voltage. So what is it? So because the windings are the only thing opposing this current, then we take the measurement from the watt meter. We call it PC, all right, the copper losses in the windings. So I squared R in the windings will equal to, say, there's no load. So it's the only thing, that's the only place where you're getting losses, which is equal to I squared R. So if we know that power, and then we know what these losses are in the windings, and it enables us to work out the current there. Work out the resistance. All right. So just know that circuit and which value we're measuring on the watt meter, either the constant losses or these variable losses. Yeah, these will be the variable losses or copper losses. Hey, these are, sorry, let me make it variable losses, depending on I, in other words, eh? All right, I think we're going to end there. We've just got a little bit left of this section, but the next section is quite short. So rather than bombard you with some more things, we'll just do the end part of this next week, and we'll do the module 4 as well. All right, that's it. All right, thank you very much. I'll see you next week. Bye-bye.